Are you able to see my slides? Hello? Are you able to see slides?
Yes, ma'am.
Okay. So, welcome back to NPTEL PMRF tutorials on the course Introductory Organic Chemistry 2 by Harina Chakrapani and Professor Niraja Deshaputre. Myself, Anisha Suresh, PMRF TF for this course from IIT Bombay. So, today we will be discussing week 8 assignments from previous year. So, here we will be dealing with rearrangements and some name reactions. So before going into week 8 assignment questions, last week we are having a doubt regarding shortcut method for Robinson annulation reaction. How to find out the product of Robinson annulation without doing the whole mechanism. So I have found out a shortcut method like how to predict the product of Robinson annulation. So first we have to align the molecules. We know that there will be two starting materials and here this will be a ketone, okay. So we should align the molecules to join the alpha carbons to beta carbons. So we will be having two starting materials. So we should align it in such a way that alpha carbon of one of the starting material will be towards the beta carbon of the other starting material. So if we are considering this starting material with respect to this ketone, this is the alpha carbon, the carbon that is adjacent to the functional group we are considering with respect to this ketone. So this is the alpha carbon, and if we consider this ketone of this starting material, here the adjacent carbon is alpha carbon and this is beta carbon, okay. So we will align in such a way that the alpha carbon will be towards the beta carbon of the other starting material. So here we will have conjugate addition, and here this side we will have aldol condensation reaction. So with respect to this ketone, this will be the beta position, alpha beta, and for this ketone, here this will be the alpha position. It will have two alpha position. This is alpha, this is alpha. So this alpha will orient towards this beta. So then we know that here these two alpha beta will undergo conjugate addition reaction. So a carbon carbon bond will be forming and this double bond will disappear, giving a single bond. So we will get here conjugate addition, a carbon carbon double bond will form. Sorry, a carbon carbon bond will form and the double bond here will disappear. And we know that here aldol condensation reaction is taking place. So aldol condensation reaction means the hydroxyl will be removed and we will get a alkene at that position. So the alpha beta carbons will react in such a way so as to give this double bond. We have to keep in mind first the alpha carbon should align with respect to the beta carbon of the other molecule. Align the molecules to join alpha carbons to the beta carbons. And the other thing we have to take into consideration is there are two steps. One will be the Michael addition reaction or the conjugate addition reaction, and the second reaction that will be taking place here will be aldol condensation. That is aldol reaction followed by dehydration to give this double bond. Is this clear? Any doubt? We have discussed in detail the mechanism of Robinson annulation in week 7 assignments when we have discussed. So here this is the shortcut method. So we will be having two starting materials, and those two starting materials will be having alpha carbon and beta carbon. Here if we are considering this ketone, this will be the alpha carbon and this will be the beta carbon. Alpha carbon means the carbon that is adjacent to a functional group. Here the functional group we are considering is ketone. And if you are considering the this ketone of the second starting material, here this will be the alpha carbon and this will be the beta carbon when we consider this side, and here this will be the alpha carbon. So we have to arrange in such a way so that we will be joining alphas with betas. We have to join alphas with betas. Clear? So this side conjugate addition will be taking place. So a carbon carbon bond will form and this double bond will disappear. And here this side aldol condensation will take place. And so here this ketone carbonyl will disappear and we will get a double bond. As it is aldol condensation reaction taking place in this side. We will see one more example. So we are having this system, and this is the conjugated ketone we are having, alpha beta unsaturated ketone we are having. So we have to join the alphas with beta. So here we will consider this ester group, and this is the alpha position with respect to the ester group, and this is the beta position. Okay, and when we are considering this starting material, this will be the alpha carbon. Sorry, when we are considering this ketone, so the carbon that is adjacent to the ketone, that is this carbon is the alpha carbon and this will be the beta carbon, and here this will also be alpha carbon. So we have to arrange in such a way that we will join alphas with betas. So here this alpha will orient in such a way that it will be near to this beta, and this beta will be near to the alpha, and these two parts will join. So here conjugate reaction or conjugate addition reaction is taking place. So we will get carbon carbon a new carbon carbon bond, and the double bond here will disappear, and here aldol condensation is taking place. So this functionality will be removed and we will get a double bond at that place. So this is the shortcut method for Robinson annulation reaction. Anyone having any doubt regarding this? Is it clear?
Yes, ma'am.
Okay. Now we will move to week 8 assignment questions. So coming to first question of week 8, what is the major product of the following reaction? So here they have given a cyclobutane substituted cyclohexanone, and they have treated it with acid medium. So what is the product that will be formed? So in the presence of an acid medium, what is probable or more likely to happen here? Any idea? In the presence of an acid, what is more likely to happen here? We are having a carbonyl and an acid. So what will happen is that this lone pair on oxygen will abstract that proton, and we will get a species like this. Now we will see what is the remaining steps that will take place. So coming to mechanism of this reaction, this is simply a carbocation rearrangement that is happening here. So coming to the mechanism, as we have seen, we are having a cyclobutane substituted cyclohexanone, and when we treat it with acid, this proton will coordinate with this lone pair of oxygen, and we will get a protonated species like this. Now what is the next step that will take place? In order to neutralize the positive charge on this oxygen, either this carbon carbon bond can migrate, or this carbon carbon bond can migrate. Either this can migrate, either this bond can migrate, or this bond can migrate. So which is more likely to take place? Which bond migration is more likely to take place, and what is the reason? Here we know there is a cyclobutane ring here. Cyclobutane rings, as we have discussed in the previous lectures, they are facing too much ring strain, because They are not meeting the 109.28 degree tetrahedral angle. Because of that, they are facing high ring strain. And if there is a chance to open it up, then it will definitely go for opening up the cyclobutane system. So what will happen here? Now the cyclobutane ring will open, and this group will migrate towards this position. This group will migrate towards this position, and it will neutralize the positive charge on this oxygen by shifting, breaking of this carbon oxygen double bond. Now what we will get here, this carbon is migrating towards this position, and because of breaking of this bond, a positive charge will be generated on this carbon. So we will get a 6 pi fused ring like this with a positive charge on this carbon. Because of breaking of this bond, this carbon carbon bond is breaking, and this carbon is going and attacking at this carbonyl. So a positive charge will be generated on this carbon. So we will get a system like this. Now what will happen when the lone pair of electrons on this hydroxyl will shift in this direction? So if the lone pair of electrons on the hydroxyl will shift here so as to form a ketone, either this carbon-carbon bond can migrate so as to neutralize this carbocation, or this carbon-carbon bond can migrate so as to neutralize this carbocation. We know that when this bond is migrating, it will give back the starting material, and we know the starting material is highly strained because of the cyclobutane ring. So this path is not favored. So what will happen when the lone pair of oxygen falls down? This carbon-carbon bond will migrate to so as to neutralize this carbocation, and we will get a 5-5 fused ring like this. When this lone pair of oxygen is falling down, we will get a ketone here, and this group is migrating towards this position so as to neutralize this positive charge or this carbocation. So here already one carbon carbon bond is there, and a new carbon carbon bond will be formed. So here this is a fused spiro fused ring that we are getting here. So this is the product of the rearrangement that is taking place here. Any doubt regarding this? Is it clear why only one possibility is taking place and not the other one? Here, why this bond is migrating and not this bond? Is that clear? Because of the strain of the cyclobutane ring, it prefers to open the cyclobutane when there is a chance to open. Because of that, this opening is preferred over migration of the other carbon carbon bond. And in this case, if this bond is migrating, we will get back the starting material, which is a strained system. So because of that reason, the other carbon carbon bond is migrating, and we will get this 5-5 spiro fused system. Any doubt regarding the mechanism?
Ma'am, what happen when there would be cyclopentane? Uh,
Here is cyclopentane.
yes, ma'am.
Hmm. So we can try it out. Here we are having a cyclopentane and a cyclobutane fused together. So in the presence of acid, first the acid will coordinate with this carbonyl. Then this migration will take place. So what is happening? We will get a 5-5 fused system like this, and a positive charge will be there at this position. and an alcohol at this position, right?
Yes, ma'am.
Now what if it is falling back, we will get the starting material. Since if we are writing in this fashion also, this will be the same starting material, right? This fashion also, the starting material will be same. So when it is breaking, and if the carbon carbon bond is neutralizing this carbocation, it will give the starting material only back. So most probably proton, there will be proton, right? That proton can fall here, and it can form a double bond at this position. Most probably it can take place. We will get a system like here hydroxyl will be there, and it will give this alkene. The other route will give only the starting material back. So most probably it will take place like this when there is a cyclopentane. Is this clear?
Yes, ma'am.
Okay. So the answer for our question, first question is, when there is a rearrangement taking place to this system, the product we are getting is option D. Any doubt? Any doubt regarding the mechanism or any the migrations that are taking place?
No, ma'am.
Okay. Now we will move to question number 2. So, what is the major rearrangement product of the following reaction? So, we have a dienone and it is treated with an acid. So, there is a rearrangement reaction taking place. Can anyone guess what is the rearrangement that is taking place in this?
It will be resonate.
There is a name for that particular rearrangement. So, anyone have any idea regarding that? Have you gone through the videos of week 8? So I will tell what is the mechanism taking place and what is that particular rearrangement. We will go to the mechanism in detail. So here it is called a dienone phenol rearrangement. So here we are having a dienone, and in the product we will get a phenol. So this is called a dienone phenol rearrangement. Dienone phenol rearrangement. The starting material will be a dienone and it will undergo a rearrangement reaction and it will give phenol. So, in the presence of acid, what will take place? In the presence of acid, this carbonyl oxygen will be protonated. And now there is a cyclobutane ring here. We have discussed that the cyclobutane is having ring strain, and if there is a chance to open up, the cyclobutane ring will definitely open up. Now it can open up in this direction also, this direction also, but both will give identical product. So we will see the mechanism. So if it is opening up in this direction, this double bond will migrate to give a double bond at this position. Thus carbon oxygen bond will break and it will neutralize the positive charge on oxygen. So we will get a system like this, and because of breaking of this bond, here a positive charge will be developed. So that is given here. Now, in order to neutralize this positive charge, this hydrogen will hydrogen will be removed, and the driving force for that will be aromatization. Here now it is not an aromatic system, and when the hydrogen will be removed so as to neutralize this positive charge, it will give an aromatic system, that is phenol. A substituted phenol we are getting. So this dienone is converted into a phenol, and because of this, this reaction is called a dienone phenol rearrangement. Any doubt regarding the mechanism? Even if the migration is taking place in this side as well, we will get the same product. Like if we are writing in the, if the shifting is taking place in the other side, it will give this product, but both of these are same only. This and this will be same. If migration is taking place from this side, then it will give this product, but this product and this product are same, they are equivalent. Any doubt in the mechanism of this dienone phenol rearrangement?
No,
Anyone?
ma'am.
Okay. So we will see the options, and the right option, as we have got from the mechanism, is option A. The dienone will be converted into a phenol. So the right option is option A. Now we will move to question number 3. Identify the major rearrangement product formed in the given reaction. So we have an acyl ester of phenol, and we are treating it with Lewis acid AlCl3 at 90 degrees Celsius. So it will undergo a rearrangement, and it will give one among these products. We will see the mechanism and we'll see what is the product that we are getting. They are asking for what is the major rearrangement product that is formed. Maybe more than one product is there, but we have to see what is, we have to find out what is the major rearrangement product that is formed in this given reaction. So coming to mechanism, and this is also a named rearrangements reaction. This is called Fry's rearrangement. So this will be converted into a hydroxyaryl ketone. So we will see the mechanism. First we are having this ester of phenol. So in the presence of AlCl3, AlCl3 will coordinate with this oxygen of phenol, and it will give a intermediate like this. Now what will happen? The lone pair of oxygen from this carbonyl will fall down, and it will leave as acylium carbocation. So this will fall down and this group will be removed, giving this intermediate and an acylium carbocation. Here we are having an acylium carbocation. Now we will be having some idea of what will take place. We have studied electrophilic aromatic substitution reaction, like Friedel-Crafts reaction. So what is taking place in the next step? Anyone can tell?
Madam, acylium ion will attack ortho position as well as para position,
Yeah.
but para position more likely.
Yes, yes. At lower temperatures, here we have given like 90-degree temperature. So at lower temperature, para position attack will be more likely than the ortho position attack. Like as we have seen in electrophilic aromatic substitution reaction, electron here the ortho position and para position will be having partial negative charges. It can attack the acylium carbocation, as we have shown in the arrow pushing mechanism here. Here this AlCl3 will, AlCl2 will leave, a carbon oxygen double bond will form, and if this double bond is going and attacking the acylium carbocation, we will get ortho product. As we have seen here, this is very unlikely at lower temperatures like 90 degree. it will take place more than 100 degree. So this carbon carbon double bond will shift in this direction, and here the carbanion that will be formed at this carbon at para position will go and attack the acylium carbocation in this fashion, and we will get a ketone. So this we will get. Now we need to regain the aromaticity. This is not an aromatic system, so this proton will be removed. It will shift in this fashion. This will remove, and it will shift in this fashion, and it will abstract H plus from the solvent, and we will get a hydroxy aryl ketone like this. So this is the mechanism for Fry's rearrangement. So a phenolic ester is converted into a hydroxyaryl ketone like this. So this is Fry's rearrangement, and this reaction take place in the presence of a Lewis acid like AlCl3. This is also similar to that of Friedel-Crafts reaction, but here um, we are having a phenolic ester, and it will be converted into a hydroxyaryl ketone like this. Any doubt regarding the mechanism?
No,
Okay. So what is the major product that is found here? The major product formed will be para, and there is chance for formation of ortho as well, but it will be minor, and they are not in 1:1 ratio. Para will be major one, so this will be the correct option. Both ortho and para will form, but ortho will be a minor product. That is the reason why we are choosing this option as the right option and not both A and B, because they have mentioned A and B will form in 1:1 ratio. This will not take place. Now can I move to question 4? Is there any doubt till these first three questions that we have discussed? If there is no doubts, we will go to question number 4. Coming to question number 4, the given reaction leads to formation of, we are having a substituted cyclobutanone, and we are treating it with H2O2 acetic acid. A famous rearrangement reaction is taking place here. Anyone having any idea what is that rearrangement? Any idea regarding what is that rearrangement? Here, in the presence of H2O2, which is a hydroperoxide, Baeyer-Villiger oxidation or Baeyer-Villiger rearrangement is going to take place. H2O2 is not forming an epoxide because this is not an electron deficient epoxide. Sorry, electron deficient double bond. H2O2 will form an epoxide when there is an electron deficient double bond. So, in the presence of H2O2 and acetic acid, we will see what is the mechanism of the reaction taking place. So, we are having Baeyer-Villiger rearrangement in these conditions that are given. So, this is our starting material. In the presence of H2O2 and acetic acid, first this will get protonated in presence of acetic acid, and the lone pair of electrons on H2O2 can go and attack on this carbonyl, and it will neutralize the positive charge on the oxygen. So we will get a system like this. Now what will happen is this proton will shift from this oxygen to this oxygen. A proton transfer will take place. So the proton on this oxygen will shift to this oxygen. A proton transfer is taking place. So we get a intermediate like this with H2O plus attached to this oxygen. Now what will take place? The lone pair of oxygen on this will fall down and one of the group should migrate. Either this should migrate or this should migrate. Which is more likely to migrate? A tertiary carbon or a secondary carbon? According to Bayer-Villiger rearrangement, which is more likely to migrate? Here, this is a tertiary carbon and this is a secondary carbon. Which is more likely to migrate? Here, this oxygen will fall down like this. Lone pair of oxygen will fall down and this tertiary means tertiary carbon will migrate and this OH2 will be removed. According to the migratory aptitude, tertiary is more preferred over secondary, and that is the reason why this carbon carbon bond is migrating and not this one. So we will get this product after removal of water. Here water is getting eliminated, and when this bond is this lone pair of electrons on the oxygen is falling down, this tertiary carbon will migrate. It will attack on this oxygen and this water molecule will be removed as per this arrow pushing mechanism. So we will get this lactone. This is the mechanism for Bayer-Villiger rearrangement. Any doubt? And the migratory aptitude for Bayer-Villiger rearrangement will be like a hydrogen will be having greater aptitude than tertiary alkyl, then cyclohexyl, then secondary alkyl, then benzyl, then aryl, then primary alkyl, and then methyl. So this is the aptitude for migration in case of Bayer-Villiger oxidation or Bayer-Villiger rearrangement. The substituents which can stabilize the positive charge can migrate readily. Substituents which can stabilize the positive charge can migrate readily, and this is the migratory aptitude. Any doubt regarding Bayer-Villiger oxidation mechanism and the migratory aptitude?
Ma'am, what is the working of ACOH here?
ACOH is this is acid, right? So like protonation and proton transfer, that time it will be helpful. Here,
Okay, ma'am.
for activating this carbonyl, it can be useful. And this case also, if proton transfer is not taking place from here, this OH can get protonated from this acetic acid. And this also ensure that epoxidation will not take place. H2O2 NOH condition, it will give epoxidation, we have learned. So H2O2 ACOH, it will prevent epoxidation as well. Any doubt?
Ma'am, H2O2 acetic acid will not favorable for epoxide.
No, no.
Okay. Then, madam, in the order, tertiary alkyl, after that cyclohexyl,
Yeah,
then after secondary.
yeah.
Cyclohexyl, it's a rigid system, madam, cyclic rigid system. It is more stabilized than secondary. How it is, madam?
Cyclohexyl. What is the reason exactly? I don't know. Maybe because there are more carbons attached to the system than that of a normal secondary alkyl. That is the reason why this cyclohexyl carbocation can be stabilized. Will be more stabilized than a secondary one.
Thank you.
Number of carbon atoms that are present in the system, and because of that inductive effect can be more in this case, I guess.
Inductive effect.
Yeah,
Okay. Thank you, ma'am. Thank you. Thank you.
welcome. So we are getting a lactone in the system like this and not at this position, because migration is taking place from this tertiary alkyl group and not the secondary alkyl. So we are getting a lactone like this. So coming back to the question, they are asking what is the major product that is formed here, and from the given options, it is obvious that this is the product we are getting. A lactone is forming and it is a 5-membered lactone. And Bayer-Villiger oxidation or Bayer-Villiger rearrangement, it always gives ring expansion. That we have to keep in mind. So very easily we can get come to this product. We are having only one ring expansion product given in this option. So Bayer-Villiger, if we came to know that this is Bayer-Villiger rearrangement that is taking place here, because there is a hydroperoxy group here. So very easily we can come to know, or in few seconds we can answer this is the question, correct answer, because only this is giving ring expansion. Bevelger rearrangement gives ring expansion product. So the correct answer is this lactone. Now coming to question number 5, which is the final rearrangement product of the reaction given below. So here a pinochle kind of system or a diol they have given, and they have treated it with H plus. So what is the reaction that will take place here? So it is clear that when there are two alcohols nearby in the vicinal carbons, it will lead to pinochle-pinocolone rearrangement, and we will see why we will get one as a major product and not the other. Here two chances are given when we work out pinochle-pinocolone rearrangement, that we will see why we are getting one as the major one. So here this is the diol that is given in question. In cyclohexane chair form, it can be written like in this fashion, right? These are coming beta, like both are coming above face. So this alcohol, this is above, this is also above. One is in axial position and one is in equatorial position, and axial is more prone to react. So what will happen in the presence of an acid? This will get easily protonated and it will remove, giving a carbocation. It will remove, giving a carbocation like this. Now what will happen? This oxygen will fall down and this methyl group will migrate. This methyl group will migrate because the sigma star of this methyl group can interact with this carbocation, like empty lobes of this carbocation, and that is the reason why this methyl group is migrating and not this carbon carbon bond. Because of interaction of the sigma star of this methyl group, which is axial, with that of the empty orbital of this carbocation, that is the reason why this methyl group is migrating and not this carbon carbon bond. This carbon carbon bond lobes cannot interact with this empty orbital of this carbocation, and this sigma star of this methyl group is able to interact with this empty lobe of carbocation and donate electrons towards it. That is the reason why this methyl group is migrating, and we will get this ketone with migration of methyl group. If we are considering like in this fashion alone, like without writing the cyclohexane chair conformation, we will reach the wrong product. Like we will think like here one of the hydroxyl will get removed as water, a carbocation will form, And when this hydroxyl or oxygen lone pairs are falling back, we might be thinking there is a chance for migration of this, as this is a secondary carbon, right? This is a secondary carbon. This is having more chance to migrate than a methyl, we will be thinking. Like compared to methyl, ethyl is having a greater migratory aptitude in case of pinacolone kind of rearrangement. So we can think that this will migrate in this fashion, and we will get here there is a methyl, a five membered ring system with a ketone like this. This product can also be expected. But when we draw it in the chair conformation, it is very clear that only the methyl group is able to migrate and not the other one. Other carbon-carbon bond is not migrating. Only the methyl group is migrating because of orbital interactions. Is this clear? Any doubt?
Madam, excuse me, madam. That methyl migration, please tell once again, madam.
Actually, here there will be free or empty p orbital because of the carbocation that is formed here, right? It will be oriented in this fashion.
Okay,
So,
madam. Okay.
so the sigma star of this methyl group, it will be interacting with this empty orbital. So this bond will break and it will migrate.
So
Clear?
methyl group migrate interact with p orbital.
Yeah, empty p
Empty
orbital
pair.
of this carbocation. Here, here there is a carbocation, so there will be empty p orbital for this carbocation. So the sigma star of this methyl group of this carbon bond, it can interact with this empty p orbital. So here the electron density will get transferred in this direction. So this bond will break and it will migrate to this carbocation. Is that clear?
Thank you, ma'am. Thank you.
Okay. So we are solely getting this cyclohexanone, substituted cyclohexanone as the major product. So out of these four options, the correct option will be option C. As we have seen, there was a possibility for formation of this five-membered ring, but because of that orbital interaction criteria, we are solely getting the cyclohexanone. So this is the product that is formed in this reaction. Coming to question number 6. Identify the final rearranged product in the following reaction. So here we are having an amide and we are treating it with bromine and NaOH in water. So what is the product that is forming, or what is the rearrangement that is taking place here? And they are asking for the final product that is formed in this reaction. So, seeing these reagents and the starting material, we can come to know that this is a famous rearrangement reaction, that is Hoffman bromamide rearrangement. The reaction that is taking place here is Hoffman bromamide rearrangement, because bromamide is formed in the intermediate step. So here we are having the amide and we are treating with NaOH, which is a base. The amide proton will be abstracted by the base. It will shift in this direction and we will get O minus, similar to that of enolate. Then once the lone pair of oxygen falls down, this carbon-nitrogen bond will attack on the bromine. Uh, Bromide will be eliminated and we will get a bromamide system. Again, there is a hydrogen on this amide. It will the base that is present will abstract that proton then this it will migrate in this direction and O minus will be formed. And once this O minus falls down, then what is happening is that the R group here, this is the R group, this R group will migrate and this bromide will leave. So what is the system that is formed here? It will result in the formation of an isocyanate. See here, N double bond C double bond O. This is called a isocyanate. Isocyanate. Cyanate. Nate. Now the hydroxyl will come and attack on this carbon, and this carbon nitrogen bond will abstract a proton from this water, and we will get a system like this. Now what will happen? The hydroxyl will abstract the proton from this acid part of this amide, then carbon monoxide will be removed. But we can see that here the bond is breaking and this part is removed. So what is that? OCO, that is CO2, carbon dioxide, it will be removed and we will get an amine. This N minus will abstract proton from water and we will get amine, and this is the final product which is an amine. Here what is happening altogether is the amide is converted into an amine with elimination of one carbon atom. Here ring contraction of the system is taking place. Here it is not a ring, but here carbon atom number is getting decreased. Here we can see that here there was 1 2 3 carbon in this chain, and in the final system there is only 1 2 carbons. One carbon is getting removed as carbon dioxide. Any doubt regarding the mechanism of Hofmann rearrangement? Here amide is converted into amine. In Hofmann rearrangement, amide is converted into amine with one carbon less. Any doubt? So coming back to our question, we were having this amide and we treated it with bromine and NaOH. We will get amine with one carbon less. The CO group will be removed and we will get this amine. So the correct option is option C. Any doubt? Is the mechanism clear? Can we go to question 7?
Yes, ma'am.
Okay, coming to question 7. Here, predict the major product in the following rearrangement reaction. So, this diketone we are treating with the base, it will give X. We have to identify what is that X. So, here we know that this is a base or a nucleophile. It can go and attack the carbonyl. It can attack here or it can attack from here. But only one side attack is taking place. So, which side? From this phenyl side or the substituted phenyl side attack is taking place? Any idea?
From amine side.
Why? This amine will be an electron donating group. So, here the electrophilicity of this carbon will be reduced. This will be less delta positive than this carbonyl. So, if the base is having a choice between two carbonyls, the base will attack a carbonyl that is having more delta positive charge. So since the amine is an electron donating group, it can donate electron density in this fashion. It is having lone pair of electrons, so it can donate electron density in this fashion. So here this carbonyl is having less electropositive character, or it is less electrophilic. So the base will be attacking on the other carbonyl, the benzene or phenyl substituted carbonyl. So now we will come to the mechanism of that reaction. And this rearrangement is called a benzylic acid rearrangement, because the final product we are getting here will be a benzylic acid. So coming to mechanism, in the presence of a base, the base will come and attack this carbonyl. And why not this carbonyl, is that clear? Here this is an electron donating group. So the delta positive charge on this carbonyl will be less. It will be less electrophilic, and this will be more electrophilic. So the base will choose this carbonyl over this carbonyl. Base will come and attack on this carbonyl, and we will get a tetracyclic or a tetrahedral intermediate like this. A tetrahedral intermediate like this. Now what will happen? This lone pair will fall down and this phenyl group will migrate. Lone pair will fall down and this phenyl group will migrate, and it will generate O minus here. So we will get a benzylic acid system like this, and it will abstract proton from water, and we will get this as the final product. So this is a benzylic acid. Here uh, phenyl, CH2 and acid. It is a benzylic acid, and because of this it is called a benzylic acid rearrangement. Is the mechanism of benzylic acid rearrangement clear? Any doubt regarding the mechanism?
No, ma'am.
Okay. So coming back to the question, these were the options that were given to us. So the final product that we will be getting according to benzylic acid rearrangement mechanism is option A. Now we will go to question number 8. Find out the major rearranged product of the following reaction. So they have given a pinnacle kind of system, and they have treated it with acid or heated. So what will happen? Pinnacle-pinnacolone rearrangement will take place in presence of acid to a vicinal diol system. Here we have a vicinal diol system. So in the presence of an acid, pinnacle-pinnacolone rearrangement will take place. We have seen the mechanism of this previously. So here it will get protonated, and one group will be here this hydroxyl will be removed and a carbocation will be formed. Then when this lone pair of electrons on this oxygen is falling down, this 1,2 bond will migrate to this carbon 6, which is having a carbocation, and we will get a system, fused system like this. Here the black bond will be breaking, this 1,2 bond will be breaking, and it will migrate to this carbon 6, where this OH2 plus OH2 will be removed. That is, water will be removed and a carbocation is formed. And here a bond will be formed between carbon 2 and carbon 6. We will see the mechanism. First, in the presence of acid, one of the hydroxyl will protonate and it will get removed as water, and a carbocation will be generated in this carbon 6. Now, when the lone pair of electrons on the oxygen is falling down, this 1,2 carbon 1,2 bond will break, and this carbon 2 will go and attack on this carbon 6. So it will lead to formation of this, which upon deprotonation, it will lead to formation of this spiroketone. Is the mechanism of pinacol-pinacol rearrangement clear for everyone? Any doubt? Any doubt regarding the product or the mechanism?
No, ma'am.
Okay. So coming back to the question, the right product we are getting is option D, as we have discussed in the mechanism of pinacol-pinacolone rearrangement. Now coming to question number 9, predict the final product of the following rearrangement reaction. We have benzoic acid and we are treating it with HN3. It will undergo a rearrangement reaction. It is a famous named reaction. So this reaction, we will see the mechanism. It is called a Schmidt rearrangement. So in the presence of an acid, we have given like HN3 is there, and proton source will also be there. So this will get protonated, and once this lone pair of oxygen will fall down, this water molecule will get removed, and we will get an acylium carbocation kind of system. Then once HN3, it will be like H plus N minus. It will attack on this acylium carbocation and we will get this molecule. So there will be a negative charge on one of the nitrogen. It will abstract a proton and we will get a system like this. Now when N2 is getting removed, here N2 is getting removed, this here N2 is eliminating, this bond is shifting in this direction, and this carbon carbon bond will migrate to this nitrogen of the amide, and we will get a isocyanate kind of intermediate here. Now what is happening, water in the system will attack on this carbonyl carbon and it will lead to formation neutralizing this amide, and we will get an amino acid like this, an amide bond and an acid. So an amino acid like this we will get, and then what will happen, proton transfer is taking place from this OH to this NH. We will get NH2 plus, and a removal of CO2 will take place and it will lead to formation of this amine. A molecule of CO2 will be removed and we will get this amine. Once again, coming to explaining this mechanism of Schmidt rearrangement, we are having an acid, benzoic acid. So this will get protonated. This will get protonated and it will lead to formation of OH2 plus here. And once the lone pair of electrons on this carbonyl oxygen is falling down, this water molecule will get removed and we will get an acylium carbocation here. Now, in the presence of HN3, this N3 minus will attack on this acylium carbocation. So N3 minus will attack and it will neutralize this positive charge on oxygen, and we will get a system like this. So it can be rewritten in this form, and one of the negative charge on this nitrogen will be uh, neutralized by the proton. So when the nitrogen, here we can see there is nitrogen. This nitrogen is a good living group. It is getting removed and this bond will shift here, and this carbon carbon bond will migrate towards the nitrogen. So we will get an isocyanate like this. Then the isocyanate is very reactive intermediate. Water will attack on the carbonyl of this isocyanate and this bond will migrate towards the nitrogen so as to neutralize it. So we will get an amino acid like this. Then a proton transfer will take place from this carboxylic acid to this amine, and we will get a positively charge on this nitrogen. So this negative charge, if it is shifting in this fashion, a molecule of CO2 will be eliminated and we will get amine. So in short, Smith rearrangement will take place in an acid system, and acid will be converted into amine. Acid functional group is converted into amine functional group in case of Smith rearrangement. And we have seen in Hoffman rearrangement, amide is converted into amine with one carbon less. Here also, acid is converted into amine with one carbon less. The one carbon is less because it is getting removed in the form of CO2. And here the reagent we are using is HN3. Any doubt regarding the mechanism of Schmidt rearrangement? Any doubt? If there is no doubt, here we are having benzoic acid. It is converted into aniline. Correct answer is option A. Now we will move to final question of this assignment set. Coming to question 10. In the reaction shown below, identify the correct combination of the intermediate P and the final product Q. So here a hydrazone is given and they are treating it with excess butyl lithium. We will get an intermediate P which will undergo reaction with this electrophile, that is benzaldehyde, to give a product Q. So they are asking to find out what is P and what is the final product Q. So these are the options, different options they have given for P and Q. So anyone have any idea which is this name reaction? Hydrazone is treated with butyl lithium, excess butyl lithium. So what is the reaction that is taking place here? It is a famous name reaction. Any idea? So this reaction is known as Shapiro reaction and the mechanism of this reaction is as shown below. So in the presence, we have treated it with excess of butyl lithium. So first one molecule of butyl lithium, here this is the most acidic proton. That proton will be abstracted and we will get an intermediate like this. Hello? So this amine proton is the most acidic proton. Butyl lithium will abstract the proton from this amine and we will get an intermediate like this. But we have excess of butyl lithium in the system. So it will abstract proton from this alpha position as well. It will abstract proton from the alpha position as well. So here also a negative charge will be generated. Two negative charges are generated. So this negative charge that is generated alpha to the hydrazone, it will migrate in this fashion and this tosyl group will be removed. This negative charge that is generated alpha to that of the hydrazone, it will migrate in this fashion as shown in this arrow pushing mechanism. Then this tosyl group will be removed and we will get an intermediate like this. Here double bond is formed. Here the double bond on this carbon nitrogen will break and a double bond is formed between this two nitrogens. Now once the negative charge on this nitrogen falls down, this bond will migrate and a negative charge will be generated here. Here there will be a negative charge and one molecule of nitrogen will be eliminated. So we will get this, as there is Li plus from butyl lithium, the negative charge or the anion will be neutralized by that Li plus and we will get the species P, lithiated species. This is our intermediate that was asked in the question. And now when we treat it with benzaldehyde, this is having like here C minus and Li plus. So that minus will go and attack on this benzaldehyde, and we will get an product like this. This is clear. But there is one mistake in the question that was given in last year assignment. They have given like, now we have seen that this is the product that we are getting, right? Sorry, that is not a mistake, I was mistaken, sorry. So we are getting this as P and this as Q. This is Shapiro reaction. It take place when there is an hydrazone and excess of butyl lithium. So in presence of butyl lithium, first it will abstract the proton on this nitrogen, and it will generate an intermediate like this. Now there is possibility. Now there is possibility for formation of like this is also acidic hydrogen, so it will be abstracted and it will lead to formation of this anion. And once this anion migrate, it will lead to elimination of tosyl group as shown by this arrow pushing mechanism. So here a double bond will form, here the carbon nitrogen double bond will break, and a nitrogen nitrogen double bond will be formed. Now once the negative charge on nitrogen is falling down, it nitrogen getting removed, and a negative charge is formed on this alkene. So it will be neutralized by the Li plus, which is the counter cation. And here we can see this will be Li plus and CH minus. So this will go and attack on this benzaldehyde, and we will get this secondary alcohol Q. Is the mechanism clear? Any doubt regarding the mechanism? This reaction is called a Shapiro reaction. So the product that is formed in this reaction is this lithium species, and then this lithium species will add on to benzaldehyde, and we will get this product. Is this clear? So this was the last question in this assignment. Do you have any doubt regarding any of the questions that we discussed today or in other assignments? And this will be the last class for this course. This was the last assignment and this will be the last class. If you are having any doubts, you can feel free to ask.
Madam, your YouTube videos, madam, that link.
Actually, YouTube links are available in NPTEL site only. NPTEL site, I will show you. I will show you how to access that. Sorry, this is old one. So you will be able to see here in the course outline a problem solving session. Like in your when you log into this NPTEL site, wherever you are able to see the videos like week 1, week 2, week 3, week 4. At the bottom side there is problem solving session, so you can click on that problem solving session. And here, if you click here to view the problem solving session lectures, it will lead to this spreadsheet. And here I have provided all the links for the YouTube videos, and also the slides are available in this drive. That link is also available here. So this week lecture I will upload, and I will share the link. So from NPTEL site only you will be able to access the YouTube links. Is that clear?
Thank you, ma'am. Very kind of you.
Okay,
Very
thank
kind
you.
of you, ma'am. Thank you, ma'am.
Thank you.